as we dive into this topic, and where we'll be discussing epidemiology. We are honored to be joined by none other than our esteemed facilitator, known to most of us, Saddrudeen Ali, a level 6 MBChB, who is going to guide us through this session. And once again, thank you for being here, and I hope you find the session insightful and engaging. Saddrudeen, the floor is yours. And before we begin, we'd like to start with a word of prayer by Jibril. Please, Jibril.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله رب العالمين الرحمن الرحيم مالك يوم الدين إياك نعبد وإياك نستعين اهدنا الصراط المستقيم صراط الذين أنعمت عليهم غير المغضوب عليهم ولا الضالين آمين.
And Saddrudeen, you can start.
Thank you so much, Brother Mustafa, for starting us off, and thank you, Jibril, and thank you to all. Thank you to the rest of you who have attended. I hope you will be able to benefit at the end of the session. And the reason why we are focusing today on epidemiology is because epidemiology comes as an essay question in your Com Health exam, and you're going to have 3 essay questions, and the essay questions, you're going to do them together with the SAQ, and it's a physical paper. The MCQs might be online. There's a good chance that the MCQs can be online, and they most likely repeat the MCQs. Mustafa, are you able to hear me?
Yes, we can hear you very well.
So in case I drop out, just alert me. So the MCQs, most likely they're going to repeat, and the guys ahead of you, the current outgoing 5th years, the MCQs were basically repeated from the past papers, and the SAQs, normally it's a written paper, and it's the one that you need to focus most on. The SAQs, you're going to have 11 questions in section A, and then you choose any 10 questions. And then now you have section B, which is the essay question, and the essay questions, remember, only 3 questions. So out of the 3, you choose 2 questions. So the first one always is either biostatistics, then the second one is epidemiology, then the third essay question comes randomly from any other topics. It can come from occupational health as an essay question. It can come from nutrition. So basically, just know epidemiology has to come in the exam as an essay question, and biostatistics has to come in the exam as an essay question. So it's basically, if you're good in both, then no need to worry about the the essay part. But then if you're not good in biostatistics, I think epidemiology is one easy part you can get your marks. So we'll start off. We're going to do it slowly, and then as we progress, it's going to get more advanced. And I usually like this approach. It's better starting to know the easy things before we get to the hard things. So we'll start by cumulative incidence. So cumulative incidence is a measure of the number of new cases of a disease or other health-related events in a specified population at risk during a specific period. So basically, the formula for cumulative incidence is the number of the new cases during the period. For example, you're studying a group for 1 year. So it refers to the number of new cases. For example, if maybe 900 people had COVID-19 in maybe KNH, then over the past 1 year, you've started studying COVID, then maybe 100 more patients get COVID. So basically, you're looking at the 100, the number of the new cases during your study period, over the number of individuals at risk at the start of the period. So let us look at this example. So for example, a study is conducted over a period of 1 year to determine the incidence of a certain disease in a population of 1,000 individuals. So at the start of the study, we assume that all the 1,000 individuals are at risk. And then you're told, during this study period of 1 year, 50 new cases of the disease are identified. So how are we going to calculate the cumulative incidence? So remember, we say the cumulative incidence is the number of new cases during the period over the number of individuals at risk. So how many new cases have we identified? 50 over the population at risk, which was 1,000. And then that one we get a fraction, 0.05. And then it's better to just convert it to a percentage. So you just do 0.05 times 100%, you get 5%. And then in epidemiology, there's always marks for explaining your answer, especially in the essay question. So you'll be told calculate and then interpret. There's always 1 or 2 marks for interpretation. So you say the cumulative incidence of the disease in this population over 1 year is 5%, means 5% of the individuals in the population at risk developed the disease during the study period. So this is very easy. Whenever you're given a question on cumulative incidence, just take the number of new cases over the population at risk. Okay, let's go to the next scenario. So the next scenario is the incidence rate, also known as the incidence density. Now, this one, it takes into account not only the number of new cases, but also the total time. This one has the aspect of total time that the population is at risk. And it is very useful. We prefer using the incidence rate when the period of observation varies between individuals. For example, you're studying, if you're studying a whole group over 1 year, we can use the cumulative incidence. But then let's say if someone falls out of the study, someone comes in, someone falls out maybe after 6 months, someone drops out after 2 years, after 1 year, and your study period is 2 years, someone comes in maybe at the last 3 months. Now the best calculation to do is the incidence rate, also known as the incidence density. And it is good for studies where individuals enter and leave the study at different times. So let us look at an example, okay? So remember, it is just the number of new cases during the period and the total person time at risk. You're going to understand how you're calculating it. So let's say we have 5 individuals. Normally, even the ComHealth notes, they normally provide this example in the lecturer's notes. So we have 5 individuals. We are studying them maybe for a period of 2 years to determine the incidence rate of a disease in these 5 individuals. So person 1, okay, person 1, after 2 years, he develops no disease. Person 2, after 1.5 years, develops the disease after 1.5 years. Person 3, at the end of your study period, which is 2 years, has no disease. Person 4, the 0.5 after half a year, or maybe after 6 months, develops the disease after 0.5 years. And then person 5, after 2 years, has no disease. So we can clearly see that person 2 and person 4 are diseased individuals. And then person 1, person 3, and person 5, they are not diseased individuals. So how are we going to calculate this? So the first thing is to identify. And that's why this incidence density or this incidence rate is more superior than the cumulative incidence, because the cumulative incidence just takes the number of new cases over the population at risk. But then this one has a total person time risk. Very good for studies that people are lost to follow up, or maybe we have such variations. So the first thing, let's get back to the formula. It's to identify the number of new cases during the period. How many new cases are here over these 2 years? We have 2. And these are person 2 and person 4. And how do we calculate the total person time at risk? So the best thing is to do what? Just take the years. It means person time at risk. So how do we take it? You just take person 1, 2 years, person 2, 1.5 years, just the time that they were studied for. Person 3, 2 years, person 4, 0.5 years, and then person 5, 2 years. So you add them all up, and then you get 8 person years. And remember, we got 2 as our numerator, then you divide by 8. And that's how you get 0.25 cases per person per year. Okay? And it means that on average, there are about 0.25 new cases of the disease for each person year of observation. Are we together so far? It's starting to get a little bit technical.
Howard.
Yes, Henry? Okay. So far, are we okay?
Yes.
So feel free to interrupt me in case you guys don't understand. So we've seen how to calculate cumulative incidence. We just take the number of new cases over the population at risk, okay? But then this one, we take the number of new cases, which is 2, over the total person time at risk. And then this one we've seen, we just take the years, okay? We just take the years, and then we sum them all up, okay? So let us look at the third thing, how to calculate prevalence. Don't worry, I'll share these notes. No need to write. We'll be moving a little bit fast because of time, okay? So prevalence means basically what is prevailing. Prevalence, it's just basically the total number of cases of a disease present in a population. And the prevalence in the MCQ, they normally ask us given point in time, which is the best study to do at a given point in time. Let's say instead of studying you guys for 1 year, how many people are passing, how many people are failing, I just come and say how many people have passed at this time, have passed their 4th year. So that is that is prevalence. So it means at a given point in time. And then that's why it includes both the new and the pre-existing cases. And it is expressed as a proportion or a percentage. So for example, if I want to check the best study design for example, I want to do a research on how many people are left-handed in the 4th year class. It means at this specific point in time, I want to know how many people are left-handed. And the best study design the best study method to use is just doing the prevalence, okay? And just the simple thing is, it's the number of existing cases. Remember, in incidence, we said new cases. Prevalence is the existing. How many left-handed people are existing in your class over the total population, okay? So for let's take this example. We're studying a population of 1,000 individuals to determine the prevalence of a certain disease at a specific point in time. And at that point, 70 individuals have the disease. So you asked, what is the prevalence? So basically, you just take your 70 over 1,000 over your total population, and then you simplify the fraction, you get 0.07. Then you can convert to percentage. So you can say 7% of the individuals at this particular point in time have the disease. So you can see, let us look at the last line here. It means 7% of the individuals in the population have the disease at that particular moment. So far, so good. If you have any questions, just feel free to type in the chat box. Now, there's something called attack rate. Attack rate, just know attack rate is just a fancy name of the incidence rate. And the attack rate is a measure used to describe the proportion of individuals who develop a disease during a specific period. Most commonly, it is used in outbreak investigation, and it is just a type of incidence. So don't confuse yourself. Whenever you're told calculate attack rate, basically they're just telling you to calculate the incidence. And the incidence rate, how do you calculate the incidence, especially the cumulative incidence? We just take the new cases over the population at risk. Okay, same thing. It's the same thing. So let us check the formula. So the attack rate is the number of new cases during the outbreak period over the total population at risk multiplied by 100%. So let us now check here. It's a trick question. Basically, if you're told also to calculate incidence, the cumulative incidence, you're going to use the same approach. So let's say there's a population of 1,000 individuals. At the start of an outbreak, let's say there's a cholera outbreak in Nairobi, we have 50 individuals out of these 1,000 who already have the disease, meaning they have the pre-existing, maybe the disease of interest. They already have the disease of interest. Now, during the outbreak period, which is the period of your study, okay, 200 new cases are identified. You're told calculate the attack rate. Let's get back to the formula. The denominator says total population at risk. Let us see. Are these 50 individuals who are already having the disease, are they at risk? No, they're already affected. So what you're going to do is, first of all, we have to get our population at risk. So we do 1,000, which is the total population, minus these 50 diseased individuals, we have our 950. And this one automatically becomes our denominator, okay? Then, what is the attack rate? We just get the new cases, which is the 200 people, new cases over 950 times 100%. So we get a fraction, 0.2105, and then we multiply by 100%, we get 21%, okay, or 21.1%. That is how you calculate your attack rate. So remember, attack rate, let it not confuse you. It is just similar to the cumulative incidence. It's just that it is used in outbreak investigations, but the formula still remains the same. So if you're told to interpret, you say the attack rate during the outbreak period is approximately 21.05%, and this means about 21.05% of the population at risk develop the disease during the outbreak period. So far, how is it, Mustafa?
And all is good, Sadru.
So we have seen how to calculate the cumulative incidence. That is the first thing we've seen so far. And we've said the cumulative incidence, we just take the formula, which is the number, the new cases over the population at risk. Remember, just to say at the population at risk. It's very important to say that. And we've seen the second thing we've known to calculate was the incidence rate, also known as the incidence density. Same thing. The number of new cases, which we had in that example, was 2 over the total person, time, year risk, something like that. So, and we're just adding the year. This one you've studied for 6 months. This one you've studied for 1.5 years. This one you've studied for 2 years. And then the third thing we saw was how to calculate prevalence. And we said prevalence means at a particular point in time. And it means the existing plus the pre-existing. It means, for example, just shika to prevalence. I want to check the number of what is the prevalence of the left-handed individuals in the 4th year class. It means you include everyone who's left-handed, whether saindo umepata, ama there was also pre-existing left-handed people. So it means you take all of them over the total population. And then we've seen now how to calculate the attack rate, and the attack rate is just similar to the cumulative incidence. The same formula. The population at risk, okay? Can see here, the population at risk, I mean the number of new cases over the population at risk. So with that in mind, now we can come here now. Okay? Now it's starting to get advanced, kidogo. So you must know how to draw this thing called a 2x2 table. Before we even look at this question, let's look at how we're going to draw a 2x2 table. You always put the disease on the horizontal margin. And you always start with disease, yes, disease, no, and always put your total. And then, for example, now you put the exposure or the risk factor, okay? We put our exposure along the vertical margin. If you draw it this way, you will never forget. Just know the disease goes this way, and then the exposure goes downwards, okay? So, and then you always start with exposed yes, exposed no, and then your total. Now, let me just try to give you another example. For example, if you're given lung cancer, okay, and then you're given smoking. So you know which one is the disease? It's lung cancer. So lung cancer will be in this horizontal margin whenever you're drawing a 2x2 table. And then smoking, you have to come and bring it here in the vertical margin, because that is the exposure or the risk factor, okay? That is how you draw it. Your disease always has to be on there. If you draw it wrongly, And then the problem with the essay question, if you get it wrong, part A, part B is tied to part A, part C is tied to part B. So you might find everything wrong. And I've showed you now how to draw your 2x2 table. So you make sure your disease is on the horizontal margin, and then your exposure is on the vertical margin. Okay, here we have the disease, here we have the exposure. So with that, we're going to calculate something called the relative risk. So so the relative risk, basically, it shows the strength of the association between an exposure and an outcome. So it compares the risk of the outcome in the exposed to the risk in the unexposed. So in simple terms, it means relative risk means you're just doing risk in the exposed over the risk in the unexposed. Okay, and then we see, for example, if you're told, if you do your relative risk and you find 1.5, if you do risk in the exposed, maybe you have here in the risk in the exposed, maybe you have 1500, and then you find that down here the risk in the unexposed is 1000, so you get 1.5, and then you're told smokers have a 1.5 times more risk in getting lung cancer than non-smokers. It means whenever it's greater than 1, if it's greater than 1, means that thing can contribute to the formation of the disease. If you get exactly 1, if you do the relative risk, it means this thing neither has any benefit nor it does not have any protective factor against the illness. Okay, but basically means it does nothing. Then let's say if you get your relative risk and you find it's less than 1, for example, you have 0.8, it means that risk factor here it's protective against the disease. For example, you may be told exercise and maybe reduction of maybe myocardial infarction. You might find that exercise is protective. If you calculate the relative risk, exercise might be protective against getting myocardial infarction. You're going to understand this. Let's look at the example, okay? And then remember, there is relative risk. Before you continue, I'm just trying to sensitize you. There is relative risk, and there's something called absolute risk. So the way mina shikanga, okay, the relative risk, it's just the same formula, but then it means the risk in the exposed over the risk in the unexposed. Then here, for the absolute, it's the same thing, risk in the exposed, but then instead of dividing, you subtract, minus the risk in the unexposed. And how do I remember this? You know, some relatives can be very toxic, so they cause divisions in the family. So that's why I say if you're told to calculate relative risk, you always divide. But then if you're told to calculate absolute risk, you subtract. Okay. So with that, let's now look at how to calculate the relative risk. So for example, you're told here in this box here, 30, we have 30 individuals who have had maybe lung cancer and they've been exposed to smoking. And here we have 70 individuals, just an example, they have the disease, they have lung cancer. I mean, they have no disease. You see, the disease says no. They have no disease, but they have been exposed. They have had the exposure. Maybe they have smoked and have not gotten the lung cancer. And total, we have maybe 100. Then here, down here, we have the people who are not exposed. You see this row here? This row here is people who are not exposed. So we have this 20. They have not been exposed to maybe secondhand smoke, but they still got lung cancer. And then here, we have people who never have no exposure to smoke and and also do not have the disease. So we have maybe the total here, 20 plus 80, we have 100. Then we have, if you calculate now the total, 30 plus 20, you get 50. 70 plus 80, you get 150. And the grand total is the sum of basically what is going across and down. And then you find 200 is the total population of this study, the total study population. That is basically how you draw your table. So Now let's go down, you see. So how do you calculate the risk in the exposed? So the risk in the exposed, we basically just, as long as you've drawn your table correctly, the risk in the exposed is these 30 individuals. They have the disease and they have been exposed to the, smoke, and they have gotten lung cancer. We just do over here, over the total here. So the risk in the exposed basically is 30 over 100. What about the risk in the unexposed? It means the people who have had the disease and they did not smoke, basically. So you just take the 20 over the total that you'll find there, just on the horizontal margin here, okay? So with that in mind, it's going to be 20 over 100. So remember, this up here is the risk in the exposed, and then down here is the risk in the unexposed. So whatever fractions you get, what are you going to do if you're told to do relative risk? You're going to divide, okay? But then if you're told to calculate absolute risk, you just minus, you subtract the risks, okay? So let's see how they did it. So you can see they got 30 over 100, which is 0.3. I don't want to confuse you by telling you A over A plus B over C, divide by C over C plus D. No. I just want you to draw the table. If you draw the table, everything is going to work out so smoothly. Okay. Let me erase a bit and repeat that statement. So whenever you draw your 2 by 2 table, just make sure you have the risk in the exposed, which is 30 over what you'll get at the end there, 100. Then the risk in the unexposed is 20 over whatever you get. You might get a different number. This is just an example. And then you divide. You divide the risk in the exposed and the risk in the unexposed. And that's basically what they did here. You can see they divided 30 over 100. They got 0.30. Then they divided 20 over 100. They got 0.20. And remember, when you're told to do relative, you just remember about the concept of division. Okay. So they divided, then they got 1.5. So it means the risk of developing the disease is 1.5 times higher in the exposed group compared to the non-exposed group. So in other words, it means exposure to the risk factor increases the likelihood of developing the disease. If it's 1.5 times as a percentage, means you're 50% more likely to develop the disease if you are exposed than someone who is not exposed. So I'm seeing something in the chat. Let me see. Won't the 70 count as exposed? No. Wait, someone is asking, can this 70 count as the exposed? No. Because when you're calculating the risk in the exposed and the risk in the unexposed, it means we're looking at who has gotten the disease, basically. Basically, we're just taking this 30 and 20, and then we're dividing by the totals here. It means this person, this group here, 30, they smoked and got the disease. And then 20 people, they did not smoke and they got lung cancer. So we're trying to compare this exposure. Is smoking and lung cancer directly related? Like, does it cause? I hope you've understood. Okay. I hope Manish, you have understood. Okay. So we're going to see the relative risk. Grace, you're going to see. Makioto Grace, you're going to see. And Lukman is asking, why 50%, yet we got 1.5%? No. We did not get 1.5%. We got 1.5 times more. You see, we got, let me erase everything. Let me just make things easy here. We got 1.5 times higher. And you understand how the 1.5 has come about. So it means we've taken the risk in the exposed, which is 0.30. We've gotten 0.20. We've divided. It means you're 1.5 times more likely to get the disease if you smoke than someone who has not smoked. So let's convert this 1.5 times to a percentage. Sindio? So if you convert 1.5 times to a percentage, how is it going to be 150%? It could be if we convert, okay, 1.5 times 100, you could say 150%, which is allowed. There's a 150% more. You're going to, yani, the percentage increase is going to be 150%. But then ideally, if you're calculating risk and everything, but it's not like 150, it's 50% more chance. Because 150, I think you maybe unless it's like 3 times is when you can say 150. I don't know come we understand how the 50% is coming. Or just say just okay, let's not confuse, okay? Let's just say just take this 1.5 and interpret it as 1.5. Just say the risk of developing the disease is 1.5 times higher in the exposed group compared to the non-exposed group. So when you get the relative risk is greater than 1, it means that exposure contributes to the disease. We can see there's a relationship. We can say cigarette smoking, even if it's you get 1.1 more, 1.1 times more, it means cigarette smoking can be attributable, can be attributed to causing lung cancer. But then if you get 0.8, the risk in the exposed over 0, risk in the unexposed, you get less than 1, it means that exposure is protective against the disease. If you're exposed to that thing, then you're protected against the disease. For example, in, I think, rectal cancer, I'm not saying you guys smoke, but the rectal cancer, it has been proven that people who smoke have a lower incidence of getting rectal cancer or colorectal cancer, okay? Especially rectal cancer. So it means now, if you get something, if you do the incidence, I mean the relative risk, you'll get less than 1. We're going to see it. And if you're told to now calculate the risk difference, the risk difference is also known as the absolute risk. And you know, this Commonwealth guys sometimes might want to trick you. If you say risk difference, someone will automatically know you just subtract the risks. So they'll bring a different word. They'll tell you calculate the, instead of calculating the risk difference, atakwambia calculate the absolute risk reduction. And I told you, whenever you hear relative, you divide. Whenever you hear absolute, it means you take the difference. Same thing. We are told, we are given this example in this box, and then we are told calculate the risk difference or the absolute risk reduction. So what do? We just take our 30 over 100. That will be our risk in the exposed. Then what do? Minus the risk in the unexposed, 20 over 100. Sindio? Now that will be the risk in the unexposed. What are we going to do? We're subtracting them. That is basically it. Okay. So basically, in short, basically the formula, this formula summarizes it. The risk difference is equals to the risk in the exposed group minus the risk in the non-exposed group. And we saw, you just take your 0.30, that is the risk in the exposed, then 0.20 is the risk in the unexposed. Then here we have risk in the unexposed. So you just minus them. So it means you just do your 0.30 minus 0.20, then you get 10%. So it means the absolute, so you just interpret just basically by describing what you are describing the question. So the absolute risk, the absolute increase in risk of developing the disease due to the exposure is 10%. Okay. Just ignore this. It's kind of complex for you guys, but just ignore that. So have we seen how to draw a 2x2 table? And have we seen the difference between relative risk and absolute risk so far? I think Kimachas has explained that question. Sawa. So far tuko sawa, si ndio majamaa? Epidemiology is easy, umeona? Okay. I hope so far we are okay. So we've seen, let's quickly recap. We've seen how to calculate cumulative incidence, where we saw it was the new cases over the population at risk. Then we saw how to calculate the incidence density, also known as the incidence rate in populations about they are lost to follow-up, or those variations where the whole group does not finish the study. We say it's basically the same thing, the new cases over the person time at risk. We just take the time in years. We just say 1.5, 0.5, etc. Then we saw how to calculate prevalence. And prevalence, we said it's a specific point in time. Then now we came to check how to calculate the relative risk. And relative risk, we said you divide. You always divide. But then for the absolute risk, also known as the risk difference, what do? We subtract. So don't forget that. And we saw how to draw the 2x2 table. The disease has to be on the horizontal line. Then the exposure has to be on the vertical line, the vertical aspect. And we've seen how to calculate the risk in the exposure. Just take the things on the left over the totals on the right. Okay. So I'm recapping again. So whenever you're told relative, okay, relative risk, you always divide by the risk in the exposed over the risk in the unexposed. Then if you're told to calculate the absolute risk, you have to get the risk difference. You subtract the risk from one another. It's the same thing. Now here, now here it's about to get a little bit technical, but then don't worry. There's this thing called the population attributable fraction, and I want you to differentiate it from the attributable fraction. Remember, one has population attributable fraction, and this is what you're going to start with. So how do we calculate the population attributable fraction? Here now, I normally call it the rule of P's, because it has P. This is the population attributable fraction. So the first thing is to find the proportion, okay, of exposed individuals. Like we need to know of the total, how many people have been exposed to this, or how many people have the risk factor of smoking, for example. So we can see here our total population is 200. I want you to pay keen attention to this. We need to know the proportion of the exposed individuals. The total number of exposed individuals are which ones? Anything across this line. So we have these people, they have been exposed and they have gotten the lung cancer. I'm just using lung cancer and smoking for easy reference. Then here we have people who have been exposed to smoking, but they did not get the disease. But then all of these people, the 30 individuals here and the 70 individuals here, basically all these individuals, these 100, have been exposed to the smoke. And the total number of individuals of our study is the bottom right, which is 200. So basically with that in mind, okay, with that in mind, the formula for calculating the population attributable fraction is you need to find the proportion of the exposed So you need to find the proportion of the exposed. And I've shown you how to calculate the proportion of the exposed. How do you calculate it? Just get the total number of exposed individuals over the total population. Okay, and we've seen how to calculate to see I've showed you how to check it in the table. Basically, you just go to the exposed, anything across that line. Anything across, like the 30 here, anything exposed going this direction, meaning the 30 individuals here, then the 70 individuals. So basically just take that, in simple terms, just take the total 100 or whatever will be here in the exposed over the total population, which is 200. That one will give you proportion of the exposed. And remember I told you population attributable fraction, P, you have to find the P first, which is proportion of the exposed. And then it's very simple from there. You just need to cram this formula. So you just do relative risk minus 1, okay? Then you multiply by the proportion of the exposed. Ukishika to this part of the formula, you will get the marks because you just replicate over the same thing now, the proportion of the exposed individuals, relative risk minus 1, and then you just do a plus 1 down here. So in short, whatever you get here, let's say this one here, this proportion of the numerator is A. You're just going to do A over A. Then remember here is A plus 1. This is a simple thing. So just look at the formula again. It's a little bit, I know my screen is a little bit blurred because it's a PDF. But then, and you see the reason why I started with teaching you the relative risk. Because if I could have taught you population attributable fraction, say mtu angekuwa anashangaa, what is this relative risk? So ideally you should do your relative risk, and I've shown you how to check the relative risk. Remember, relative comes from the word relative, so it means you're going to divide the risk. So it means you have to find the risk in the exposed over the risk in the unexposed. That gives you your relative risk. So you just do relative risk minus 1. Just put it in bracket. You multiply by the proportion of the exposed. Then you just do the same thing. The proportion of the exposed, relative risk minus 1. Then you just do a plus 1. So let's say this, we call it A. So you're just going to do A over A plus 1. So with that, let us see stepwise how it was done. Okay. So let me clean it up. So, okay. So how do we calculate the proportion of the exposed? Basically 100 over 200. That is the proportion of the exposed individuals. We multiply by what? The relative risk. The relative risk, we just do our 30 over 100 divide by 20 over 100. Then we just do the same thing, numerator, denominator, plus 1. Let us look at how they did it. So the first thing, they got the proportion. Whenever you're told population, whenever you're told population attributable fraction, what do? We just do proportion of the exposed first. This is the first thing you do. If you don't do this first, you're going to most likely you're going to forget the formula. So how do you do the total? You just do the total exposed over the total population, and I showed you how to check it, 0.5. Then ignore this A over A plus B. I've showed you the way how to do it. So just do your 30 over 100. You get, this is the risk in the exposed. Then you just do 20 over the total, which is 0.20. Then we are told to calculate the relative risk. So you get 1.5. So basically just replacing, and you say the formula is the proportion of the exposed, which is now we've got as 0.5. So we just do 0.5 over the relative risk we've gotten is 1.5 minus 1. And then we just replicate the same thing over 0.5 into bracket 1.5 minus 1, then close bracket plus 1. Basically, that's the same thing they did here. And you can see here 0.5 times, which is the proportion in the exposed times 1.5 minus 1, the same thing, and then just that plus 1 there. So after you work out all that, you're going to get it as 0.20. You can convert it to a percentage times 100%, and then you get 20%. So it means 20% of the disease cases in the population can be attributed to the exposure. Yani, if we get 100 sick individuals, 20 of them have gotten the disease because of the exposure and 80 have not. So it means if we basically in other terms, in more technical terms, it means it's called the population attributable fraction. You can say 20, if you get 20%, if you get 60%, you can say 60% of the diseased individuals have the disease because of the exposure. And it means if we eliminate the exposure, let me clean this up a bit, and you look at the last statement. If the exposure was eliminated, the incidence of the disease could reduce by that percentage. Okay. So have we understood how to calculate the population attributable fraction? I'm going very slow, by the way. We might extend. Are we comfortable? Don't worry, I'll send you.
Yes, we are, Saddru.
So do you express the incidence? Someone is asking, do you express the incidence rate as a percentage? Yes, you can express it as a percentage. So far, tukoaje majama? Are we okay? Are we okay there?
Yeah.
So just remember, there is population attributable fraction. Now there is attributable fraction. Now attributable fraction can be a little bit confusing because this one now, it's like a mixture. When, sometimes if you see, most likely they're going to bring population attributable fraction. Like this is going to come like 80% of the time, 100% sure. This one is good. You're going to be asked this one is in your upcoming exam in a week or 2 weeks time. This one is going to come. But then just in case they switch on you, this one hasn't been taught, but I just added it. It is something called the attributable fraction. So attributable fraction, basically, it's like you're doing a risk difference and then you're dividing. You can see it has a minus component and it has a division component. So basically the formula is you just take the risk in the exposed over minus the risk in the unexposed. Is this hinting you at something? Is this hinting you at something? It means you just take the risk difference, also known as, what is the risk in the exposed minus the risk in the unexposed? Known as, it is known as, yes, absolute risk. Tuko pamoja, nice. So it's known as the absolute risk. In short, you just take, confuse na hizi formula. Life is simple. You just make things simple for yourself. So it's just the absolute risk over the risk in the exposed. Unarudi huko juu tena. Risk in the exposed over the risk in the exposed. That is basically the attributable fraction. But whenever they say population, just know you have to take the proportion of the exposed individuals. Then you do relative into bracket, you multiply by relative risk minus 1. Replicate the same thing in the denominator, you just add 1, then you divide them. So whenever you're told to do the attributable fraction, haina p. So just know it's a little bit simpler. You just take the absolute risk, also known as the risk difference. Then you just divide by the risk in the exposed. So for example here, if I'm told to calculate let me just erase it. How will I go about this if I'm told to do now the absolute risk? I mean, if I'm told to do the attributable fraction, how am I going to go about it? We've said it's the risk difference. So I'm going to take the risk in the exposed, which is 0.3. The risk in the unexposed, which is 0.2. So I do 0.30 minus 0.20. I get 0.10. And then what do I do? 0.10 divide by the risk in the exposed, 0.30. Someone with a calculator can do it. Unfortunately, I don't have a calculator. Let me just open my phone. So 0.10 divided by 0.30. Yeah, you get 0.33333, which is 33%. So you can say clearly the attributable fraction is 33%. That is very simple. And you can see it's so different from the population attributable fraction. The population attributable fraction here, using the same table, we got about 20%. So it means it's two different things. So remember, whenever you say population attributable fraction, we mean P. What do we mean? We mean you have to calculate the proportion of the exposed, okay? If you're told attributable fraction, just get the risk difference over the risk in the exposed individuals. Okay, let's move to the next. I think we're almost halfway. It's going to be a long one, but I think think I'm going so slow, and as long as you're listening keenly, you would understand. Even if you don't listen keenly, I think I'll send this document. It'll help you as a guide. So let's look at the odds ratio. So pale tumefika, you can see if you don't know how to draw a 2x2 table, you're finished. You're finished. But don't lose hope. So Siad Salma is asking, how will you describe the interpretation of AF? I mean, the attributable fraction. So attributable fraction, we said, here after doing all this, we got 0.33. So we just do times 100. And then you say 33, 33% of the, you just say 33% of the diseased individuals are attributed to the exposure. Just say that. Don't say in the total population. If you say in the total population, you're talking about the population attributable fraction. Remember here, we did not take the total population here. The total population, I think in the table was about 200. Yeah, it was about 200. And we did not mention we were not referencing to the total population. You can just say 33% of diseased individuals can be attributed to the exposure. Just say that. But hautasumbuliwa hivyo. So calculate odds ratio using a 2x2 table. So odds ratio is very easy. So let me show you the formula for odds ratio. So formula for odds ratio, it's very simple. Don't even think about it. A times G. You see this 30. You cross multiply by 80. And this one is going to be the numerator. Okay? Because it has the exposed. And it has this 30. It has people who have been exposed and they have gotten the disease positive. They have exposure positive, disease positive. Okay? Simple way of calculating odds. It's the easiest by the odds ratio. Then what are you going to do? You're going to do 70 times 20. Then this one is going to be your denominator. So basically how to calculate odds ratio, cross multiplication. 30 times 80. And you know, don't reverse it the way I've showed you. This box here is the disease of interest because these are people who have smoked and have gotten the disease. These ones have to be in the numerator. Then you're going to divide by 70 times 20. As long as you've drawn your 2x2 table correctly, that is just basically how we calculate odds ratio. We cross multiply. The same thing, it's a lot of, just ignore these formulas. You can see, where have my present, are you able to see my screen?
And yes, we can.
Unfortunately, it has disappeared from my end. Let me try to, okay, it's back now. Hey. Okay, hey. I think someone is, okay. Okay, so basically just do your 30 times 80 over 70 times 20. So you get 2,400 over 1,400. So you just say your odds ratio. This one you don't need to convert to a percentage. Odds ratio, it's just a ratio, okay? It's not a percentage. Just convert it to, it's just, you just simplify it. It's a ratio of this to this. So it means it's 1.714. And you just say the odds of developing. By the way, when I told you interpret, rephrase the question. The odds of developing the disease are 1.714 times higher in the exposed. Remember the exposed group and who got the disease were in the numerator. They are more, like by 1.714 compared to the non-exposed group. Okay. And odds ratio, you're going to be asked in your MCQs, is a measure of association in which type of study? It's case controlled study. Okay. So far, are we okay there? Let me see the chat box before we continue.
Yes.
Yeah, so I think hakuna questions. I think people have understood, sindio? Okay.
Yes.
Now I think we are coming to almost now. We're almost winding up. We're going to do now, you're told to do sensitivity and specificity of a test. Okay? So we are told, by the way, you're not going, they will never draw the table for you in the essay question. We have to draw the table for ourselves. Okay? So let me start, and then someone will be filling for me the boxes. So different people can volunteer. So we said we have here, let's assume we have a test for a certain disease with the following data. You're told, just ignore this, okay? Okay, they've given you the hint. There are people, there are 100 individuals, they have the disease present, and we have 200 individuals who do not have the disease are absent. And then we are told these are the true positive. Now, this is the number of true positive, false negative, true negative, false positive. How are we going to construct our table? So let's make it so simple. We always say the disease, huko, sindio? Then we say the exposure, huko, sindio? So always the disease is at the top and it goes horizontally. So let's just draw. I'll just draw my table here, disease, positive. These means people who have the disease. Let me just, okay, let me just draw my lines, okay? And these are the individuals who have no disease, okay? And then here, maybe I'll put my total. Then here is my exposure. So you're told, this is from this information now, people with disease present, there are 100 individuals. So total here, down here, I have 100. That is how you construct your table. You just, ni kama tic-tac-toe, pole pole tu, ukusikuwa na haraka. If you draw the table wrong, you've missed everything. Okay, then we have people who, the total number of people with no disease, it is 200 individuals. Just draw here 200. So next, you're told 85 individuals correctly identified as having the disease. So here, it's either our exposure or the tests. And then test here, we just put positive, negative. Always start with the positive, negative. And you've been told 85 are correctly identified as having the disease. So where do you put our 85? Someone to volunteer? Someone can unmute.
Top left.
Top left, correct. Perfect. That is 85, it's going to be there. So we can easily get the difference. 100 minus 85, 15 individuals. They tested negative, but they have the disease. And here, yeah, it's true. Even without that information, they can give you, they can remove this and tell you to do the math and feel for yourself. So let us look at the true negative. True negative means, it means you're tested for HIV, you don't have HIV, and you also tested negative. It means two negatives, isn't it? True negative means you have two negatives. You don't have the disease, and you also tested negative for the disease. Where are we going to put these 108 individuals? Down here. Because kwa hii box, you can see there is negative above, there is negative. It's like a Sudoku. I don't know if you guys have played Sudoku. Minus, minus. And then you're told false positive. False positive inamaanisha nini? Someone does not have HIV, but has tested positive. Means you have tested positive on the test. The test is here. Anything across this arrow is the test, positive. So it means you have tested positive, but if we look at the disease here going down, you do not have the disease. And that means those are false positive. So 20. Then now you calculate you remember now, you want to draw table, see ngumu, very easy. Then you do 85 plus 20, you calculate your total here. 180 plus 15, you calculate your total. Then you add everything across horizontally, then you put your grand total there. And that is how they came up with. I don't know why my screen keeps on disappearing. Oh my goodness, my screen. Are you guys seeing anything?
Give it a second.
Okay. Hey, it has zoomed out. I think it's because I'm using these touch screens. It's a little bit. Okay. Basically, have you understood how this table has come about? I don't know if you can be able to see my screen. So it means we got our 85, we got our 15, we got our total, we got 20, 180, 200, then we added now across. This one we got 105, 195, 300. It's very critical you know how to. Let me reload. Okay. Hi. Ebu, let me try stop sharing and then let me share again. I don't know. I can't find my marker. Let me just stop sharing and then I share again. Share. Just bear with me. I'm sorry. I don't know what happened. Let me just share again. Don't worry. Now we're almost done. We're almost done with epidemiology now. Okay, I'm back. I think I'm back. Yeah. So, but okay, have you guys understood how we've come up with the table? So you always put your disease. This one you have to know. It's the golden rule. You always put your disease across. Then anything else, you just put it down. And then positive, it comes to this box. Negative comes to this box. Okay. So with that in mind, let's now calculate the sensitivity, the specificity, those things. Okay. The true negatives and the false negatives we've seen. Now let us look at how to calculate sensitivity and specificity. So sensitivity means the proportion of true positives among all individuals with the disease. So remember when you were saying relative risk, should we go across? Now, the only place in epidemiology where we go down, okay, just note, is in sensitivity and specificity. Just know that. And what is the sensitivity? The sensitivity means we just take the true positive over the total disease. Yeah, it means the proportion of the true positive over the total. So if you're told to calculate the sensitivity, the only time in epidemiology where we take this 85, and we go down and we take it over 100, it means we're only doing it in sensitivity and specificity. So when you're told to do sensitivity means sometimes you might be even asked to define these things in your SAQs. Ukishajua concept, it means you take it's the proportion of true positive over the total diseased individuals, the people with the disease present. And the sensitivity, the specificity means you take the proportion of the true negatives. Okay. And this is the only time we have to vary a little bit. Instead of taking the 20, we take the 180 because these are the true negative. And the true negative, it's the specificity. Sensitivity, true positive. Specificity, true negative. So we take the 180, then you do over 200. So let's look. You can see we just do 85 over 100. You get 0.85 or 85%. And that is the sensitivity of the test. You can see. So here they just took the 85 over 100, the total. So the only time, whenever you hear sensitivity and specificity, just know your mind should readjust yourself. So just take the true positive and you go down to the total. If you're told specificity, true negative, and you go down to 200. You get that fraction, you can multiply to a percentage. And you can see here they got 180 over 200, 0.9 or 90%. So we can clearly say the sensitivity is 85% and the specificity is 90%. It means basically sensitivity is the true positive rate and specificity is the true negative rate. So now comes this catch. You're told to calculate positive predictive value, negative predictive value. It looks very intimidating. So positive PPV and NPV, isn't it? But let me tell you, now this one, we reverse our thinking back to default, okay? So how are we going to calculate the positive predictive value? Let me show you from the table. Very easy, okay? The positive predictive value and the negative predictive value. Now you just take the same thing. We just take our true positive and we take our true negative. True positive, now we go across. You remember how we are calculating the risk in the exposed over risk in the unexposed? So if you're told to calculate the positive predictive value, remember this is positive. We just take 85 over 105. If you're told to calculate the negative predictive value, we just take 180 over 195. Let's see. Let us see. You can see 85 over 105. They got 0.81 to a percentage, 81. And then the negative predictive value, 180 over 195, which is 0.92 or 92%. Okay. Sometimes you won't be told, and then what does it mean if you interpret? Positive predictive value means given a positive test result, there is 81% chance that the individual has the disease. And then negative predictive value means given negative result, it's just the opposite. There is 92 probability that the individual does not have the disease. So guys, have we known the difference of how to calculate sensitivity, specificity, the positive predictive value and the negative predictive value? Let me just recap. If you're told to calculate sensitivity, specificity, your mind should reverse. Just take this, you go down. If you're told to calculate specificity, just take 180, you go like that. If you're told to calculate positive predictive value, negative predictive value, just go across the way you're calculating the relative risk. Sorry, it's not this 15. It's supposed to be the 180. You go and divide by 195. Are we clear there? Are we clear? Now comes the last part. You're told to calculate, then you're told now to calculate the overall accuracy of the test. Accuracy of the test. How do we measure the accuracy of the test? Do you remember the odds ratio, how we were doing the odds ratio? But then let me show you the accuracy of the test you're going to do. You're just going to take this box diagonally. You see this line? You just draw like that. Accuracy of the test means take your true positive, take your true negative, you add them, then you divide by the grand total. So you're going to do 85 plus 180 over 300. So, and you can see here, you just take the true positive plus the true negative over n. So remember, odds ratio, you are multiplying. See, 30 times nini over this times this. And the one, and you can positive disease and positive exposure was in the numerator. Now for accuracy of the test, you just take the true positive, and I've shown you where the true positive is, and the true negative. Then you divide by n, and n is the total number of your study population. I think now we have come to the end. This is biostatistics. So any question? Have you guys understood it? Basically, you're not going to find any other question in epidemiology. Just what I've taught you guys. Maybe you might miss the attributable fraction, and don't forget the formula for the population attributable fraction was the proportion of the exposed relative risk minus 1. So you duplicate the same thing down here, and then you just do plus 1. That is the population attributable fractions, But what about that? If you ask attributable fractions, they don't ask it mostly. But then if you, just in case they told you attributable fraction, it's basically the risk difference over the risk in the exposed, also known as the risk difference of the absolute risk, or the absolute risk reduction. And we saw how to calculate and I showed you how to calculate sensitivity. Let me just repeat again: sensitivity and specificity. Okay. So sensitivity and specificity. Sensitivity, you go down. Whenever you see specificity, you go down. But then positive predictive value and your negative predictive value. So quick recap before you guys start asking questions. I think just to confirm we've covered everything. So we saw how to calculate the cumulative incidence, and it means the number of new cases over the individuals at risk. Then we saw the incidence rate, good for studies that when individuals enter and leave the study at different times. Then we checked the prevalence at a certain point in time. It's just the number of existing, any new and pre-existing over the total population. Then we saw attack rate, which is just a fancy name for the cumulative incidence. Then we came and checked how to draw a 2x2 table, and then we've seen how to calculate the relative risk. And remember, we said relatives divide people. So relative risk you divide, absolute risk you subtract. And that information led us to calculate the risk difference is also known as the absolute risk reduction or the absolute risk. Then we saw how to, this is just reiterating those things. Then we saw how to calculate the population attributable fraction. P means you start with the proportion of the exposed, and the proportion of exposed is 30 over, no. The proportion of the exposed individuals is 100 over 200. Whenever you get that, now sasa you do the into bracket, relative risk minus 1, you replicate the same thing on the denominator, then plus 1, then you divide. And then I showed you how to calculate the attributable fraction. The attributable fraction, basically you just take the absolute risk, also known as the risk difference, over the risk in the exposed. Then we saw the odds ratio, where we were calculating 30 times 80 over 70 times 20. Then we came now to sensitivity and specificity. Sensitivity and specificity, I showed you how to calculate it. Sensitivity, specificity is the only time where we go down. And then positive predictive value, negative predictive value, we go across. And then we talked about accuracy of the test, which means you just take the true positive and the true negative divided by n. So I think we have come to the end. Let us see any comments. Are you supposed to write the formula? Not necessary. They just need they need to work. Okay. No need to write the formula, but then if you write it, maybe you might not forget it. Hey, someone is telling me. So repeat incidence rate, Kimachas. So incidence rate, Kimachas, I don't know if you can maybe listen to the recording, but let me just repeat. So let me just repeat. Incidence rate, also known as the So incidence rate is also known as the incidence density, and it's good for populations whom like you can't study at a go. Okay, it's good for populations you can't study at a go. For example, you can see here, if I take maybe people in your class and I say how many people are going to get the cold or the flu in 1 year from now. So what I'm going to check, I'm just going to check the number of new cases during next year time like this. I'm going to check how many people develop flu, then number of individuals at risk. At risk means the people who do not have flu at that time. Let's say if your class is 1,000 people, let's say 100 have the flu already, then I'm going to see out of this 1,000, how many don't have flu? 900. This is the population at risk. Okay, this is the population at risk. So it means I'm going to see out of this 900, how many people have developed flu. Let's say if I get 100 people, let me just use a different number. Let's say I have 400 students getting flu next year time like this. So what's going to be my incidence rate? 400 over the population at risk. Remember, it's not the 1,000, it's the 900 who do not have the disease, then times 100%. And I'll see how many that's the incidence rate. Okay, you can convert it to a percentage by multiplying by 100, or you can just leave it as a fraction like this. Okay, like this. So but then imagine now you have this kind of study. Let's say the same 1,000, maybe it's not, this is not used for many individuals, this is just used for few individuals. Let's say I'm studying now flu in 20 individuals in your class, for example, or let's say 5. Let's just use the number 5. Mostly they're going to give you 5. And then out of these 5, one person after 1 year drops out. Then after 1.5 years, some other person comes in to join the study group. At any time I have 5. So you see people coming in, coming out of the study. You cannot use the incidence. You cannot use the cumulative incidence. People transferring, people dropping out, people taking a retake. Sasa here, you have to use a different a different calculation. It's known as the incidence rate or the incidence density. So what do? I just take the number of new cases, then over the total person time at risk. So here, you're given an example. I'm studying 5 students. Student 1, after, and my study, let's say, is over, I'm studying these 5 students over a period of 2 years. So person 1, after 2 years, no disease. Person 2, after 1.5 years, develops the disease. Person 3, after 2 years, no disease. Person 4, after half a year, develops the disease. Person 5, after 2 years, there is no disease. So basically, what you're going to do, you're going to just take look at the formula here, the number of new cases. Okay, the number of new cases are how many? In these 5 people, we just take this one and this one. These are the people who have developed the disease. 2 over the total person time at risk. In short, just add the years in decimals. So you're just going to take person 1, 2, which is going to be 2 years. Person 2, 1.5. Then person 3, 2 years. Okay. Then person 4, 0.5 years. Then person 5, you add 2 years. You add all this. Basically, it's here. So you just take the 2 people, this is going to be our numerator. Our numerator is going to be 2 over the total person time years. So you just do 2 plus 1.5 plus 2 plus 0.5 plus 2, you get 8. Then you do 2 over 2 over 8, then you get 0.25 cases per person. Here means there are 0.25 new cases of the disease for each person year of observation. Technical terms, but just andika to the incidence rate is, if you're told to interpret, now you don't know anything, just say the incidence rate is 0.25 cases per person year. So I hope you have understood that. You can still go through, anyone who has not understood can still go through the recordings. Okay. Let me scroll and see any comment. And you've seen the approach we've used. We have gone slowly by slowly, starting with the easy things before we went to the technical things. Formula you can write, but then just know the calculation matters a lot. Thank you. You are an amazing teacher. Will you please share your biostat notes as well? Actually, honestly speaking, I was not very good in biostats. So unfortunately, my notes, I was trying biostats, but I was not understanding it. So I put more effort in the other units, and you can see my notes here. I think biostat is just very shallow. Hata sikufika the gist of it. I was just doing the mean, mode, coefficient, interquartile range. I was just there. You see, I just left it at here. So, but I'll still share this document. Biostat is not, I didn't even touch it. But I think there was a session by Adnan with the 5th years. I think you can also request. Maybe they can take you through biostats, because if you're taken through biostats, Ama, you listen to that recording. I think it's better you listen to the recording that I think the academics team organized. Biostats, I think if you just have biostats and epidemiology like this, you don't need to worry in your essay. You just focus on your SAQs. Then incidence rate I've repeated. Attack rate I've said. Yeah, thank you. Okay. I think anyone with any question before I can hand over to the academics team. Sorry, the session was a bit long. I just wanted to nail it in one session. Okay, you're welcome. Any other question, any comment, any addition? So I think now I can leave it to, and take it back to Mustafa. Mustafa, the floor is yours. And
Thank you. Thank you, Brother Sadru, and a heartfelt thanks to you and to our presenter Saddrudeen Ali for expertly guiding us through today's topic. And thank you for your time, effort, and invaluable insights. I really benefited on behalf of myself. I really benefited from this session. Thank you so much. And many thanks to all those who attended and contributed to our discussion. We truly appreciate your time and engagement. And with all being said, and subhanaka Allahumma wa bihamdik, ashhadu an la ilaha illa anta, astaghfiruka wa atubu ilayk. Assalamu alaikum wa rahmatullahi wa barakatuh.
I also want to thank you guys. And in case of anything, just don't panic. You know, the exams are just exams. Even me, I'm panicking. I'm in sixth year. So don't worry, it's part of life. You have to be anxious hapa na pale. So I think, don't worry, just go through past papers now. I think prioritize going through MCQs, SAQs, clinical skills. Just focus on just doing more of questions. Right now, stop taking notes, stop reading notes. Just go through papers and go through MCQs, go through SAQs. Make sure I think you've been taken to the ward. We've been shown you how to do the clinical examinations and how the OSCEs are a rough idea of how the OSCEs are going to be. In case of anything, you can still request to be these sessions to be organized. So I just want to wish you all the best in exams, all the best, and yeah, you guys. I'm hoping you guys are going to. I'm very confident you guys are going to pass. Sawa. I think other than that, thank you to the academics department again. I think you guys are very lucky having these sessions. Sisi hatuko na hizi sessions. So I think in case of anything, you can just reach out to Kina Mustafa. Maybe they can organize more sessions with the other presenters, other moderators. Yeah, both of the wards and these online sessions. Sawa. Sorry if I took more time, and I think we can stop the meeting now.
Sure. Good luck guys in your revision and in your exams, inshallah.
Thank you so much, Brother Mustafa. Thank you.